Welcome to the second part of the review for Chapter 2 for Calculus, Graphical, Numerical, and Algebraic. Today we're going to be covering 2.5 to 2.9, which is all the way from complex numbers to solving inequalities. I'm going to be recording this in 2 sessions because last time it took 72 minutes to record the whole thing. I nearly died. No, I didn't. But it was not fun, right? So now I'm just going to this is what's gonna happen. So for every problem, I'm gonna do maybe 1 or 2 problems, right? Because this one they're simplified. 1, 2, 3, 4, 5, 6, 7. There's 7 simplified questions. I'm not gonna do all of them. I'm gonna do probably 1 of these and 2 of the other ones, right? So and then the rest I'll let you do, and then I'll solve them really quickly while you do them. So you'll do them, and then I'll be like, pause the video right now if you want to do it, or keep the video on, and then I'll just mute myself, or I'll just like not talk, and then I'll do the problem, right? And then if you guys get the correct, if you guys get the right answer, great, it's a review, right? If you don't, then that's kind of sad. But I'm just gonna be doing them quickly. I'll still be explaining them like in the past, but I'll be doing them quickly and without any no hesitation, right? So let's go. So what are complex numbers? A mistake already. Complex numbers appear in the form a plus bi, where a and b are real numbers and I is the square root of -1. Right? So they're real numbers, and the real numbers are square roots, the positives, the integers, the rationals, the fractions, right? They're all real numbers, but the square root of -1 cannot be obtained any other way other than some special computer stuff, quantum mechanics, I don't know, or like other real life applications that I just don't know yet. But imaginary numbers are like that, complex numbers, right? So first question is, find the values of a and b that will make the equation true. First of all, we have 3 plus 5i minus 1 plus 2i is 8 plus 3i. This is simple enough. This is just minus 1 minus 2i. 3 plus 5i, right? Distribute the negative, and that'll get you 2 plus 3i. So a is 2 and b is 3. Second problem, 8 minus ai plus b minus I equals 3 plus 2i. So this problem, you'll actually solve this equation like this. You will have 8 plus b is equal to 3, and then you will have minus a minus 1 is equal to 2, right? Because you gotta keep in mind all of the signs, right? And then I'll let you solve this right now. Meanwhile, I'll solve this. This is a little bit harder. So you gotta multiply them all out first, right? So this is 4 times 3 is 12. Is it even on the screen? Sorry, I just ate. Plus 3ai. And then 4 minus 5, that's minus 20i. And then we have ai minus 5i, so minus 5i squared. That's equal to b minus 14i. And 1i squared right here, I'll tell you right here. I squared is minus 1, so just put minus 1 here. Minus 1 times minus 5 is 5, times 12, plus 12 is 17. So we'll have 17, and then this is plus 3ai minus 20i, that's plus 3a minus 20 I is equal to b minus 14i. So I already know that I won't have enough space for this, so I'll just move everything up here quickly. There you go. And then I'll do this, and then I'll do this. There you go. So we have b minus 14i right here. b minus 14i will be equal to this. So b, you can automatically see, is 17. Right, this isn't the a plus bi in the b, but it could be, right? And a is 3a minus 20 is equal to minus 14, so 3a minus 20 is equal to minus 14, and if you solve that, a is 2. So a is 2. So those are our answers. right? And if you solve this correctly, you should have gone a is equal to minus 3 and b is equal to minus 5. And that's it. Next, we have simplify. Now, simplifying, like, okay, this looks pretty nice. It looks pretty nice. But it's not nice. It's not nice enough. We gotta make it in the form a plus bi, because a plus bi is like the standard, the most simplified form you can get. It's the creme de la creme. It's the best, right? And you can't get any better than it. So simplify, right? It's just a lot of multiplying. I'm gonna do this example because this example looks a little harder than this example. What I'm gonna tell you is multiply by the conjugate. And what's the conjugate? The conjugate is you take the denominator. No, the conjugate of any a plus bi is a minus bi. So complex numbers, whenever you have the conjugate, if you add by the conjugate, if you subtract by the conjugate, and multiply by the conjugate, you will, well, it depends on what ways you subtract and divide. And it depends on what way you subtract, not divide. You will get the real number. You will get a real number, right? So it won't be imaginary anymore. So I'm gonna tell you that the conjugate, which is denoted by a line, so we have z is equal to a plus bi. So z line, which is the conjugate, is equal to a minus bi. Right? So by that, try to figure this out. I'm gonna be doing try to figure this out as well. I'm gonna be doing this because this is hard. Okay. So first of all, we're gonna multiply all of these out. As you can see, these are actually really nice because these are already conjugates of themselves, and these are already no, never mind. Wait, no, they are. Yeah, these two are basically already conjugates of themselves. I just didn't put 2 plus 3i and 2 minus 3i, but when you take the two, they're not formally conjugates, but when you take the 2 times 3i and minus 2 times 3i, they cancel each other. So these are the difference of squares, and the difference of squares are always going to give you a real number. So this is going to be 4i, and this is going to be 9i squared. 9i squared is minus 9. Right, I'm gonna be doing a lot of this in my head, so if you're not comfortable doing it in your head, right, this is minus 9, so 9i squared. If you're not comfortable with doing it in your head, you can just work it out. And then this is 3i, and then this is I times I, which is I squared. I squared is minus 1, and then that's minus 4. Right, so this is the equation right here, and this is really nice because the I cancels out as well. Right, so the i's cancel out. You'll get 4/3 times, or rather 4 times minus 13. Okay, there you go. 3 times minus 5, which will get you the final answer of minus 52 over minus 15, which is 52 over 15. Okay, if you guys haven't worked these out yet, this is kind of like a special thing that I put in that probably won't be on the test because it would be too hard. Right, if you guys haven't worked these out yet, this is equal to 10. 9 minus I squared is 10 over, but no, this is 10 minus, this is 10, no, I got it wrong. The bottom is 10, right? This is 9 minus I squared. The bottom is 10. The top is 3 times I, minus, so positive, so that'll be 8. And then minus 3, that's minus 6. So then you will get, that's equal to 4/5 minus 3/5 I. And that's your correct answer. That's in the a plus bi. Right, this is the same thing. 2 minus I. I'm going to work through this really quick. So what you should finally get is, if I even did this right, you should finally get 6 over 5 plus 12 over 5i. And you're almost never going to get a nice answer. I don't even think that fits in the screen. Oh, it did. It barely did. You're going to get 12 over 5. 6 over 5 plus 12 over 5i. Okay, simplify and put in the form a plus bi. So in the video, you probably already know that the square root of -1 is equal to I, but the square root of -2 is not equal to 2I. Not equal to 2I. It's actually equal to I square root of 2. And the reason why is, well, this is I, this is square root of -1, and then this is square root of 2. So when you multiply them together, you'll get square root of -2. It's that simple. If you have 2 in there, it'll be square root of 4 and square root of -1, which you multiply together, it'll be square root of -4, which we actually have right here. So we can turn this into 2I instantly, and we can turn this into I. So it'll be 3 plus I, 2 plus 2I. And you guys can work that out. Right, this is a little trickier because it's square root of -8. It's I square root of 8. This will be I square root of 8, which is simply I actually recommend you put in the I square root of 8 form, but if you don't want to, you can do this. 2I square root 2. That works as well, right? Because of the simple exponent, no, radical simplification. There you go. Try to find the right words. So this is 2I square root 2, and I'll do this. So 3 times 1 is 3. Minus 2I square root 2 times 1 is minus 2I square root 2. 3 plus 2I is plus 6I. And then 2I square root 2 times 2I minus 2I square root 2 times 2I is minus 4I squared square root 2. Right, and this will give you 3. Now this will give you, wait, okay, we gotta combine this and this first. So minus 4 times minus 1 is 4. So plus 4 square root 2 this time. So your final answer would be, the A of the answer is 3 plus 4 square root 2. And the B of the answer is plus 6, right? Plus 6 minus 2 square root 2I. And that is your A, and that's your B. So this is pretty tough. It probably won't be on the test, let's be honest. But this is your final answer for your, oh god, I'm sorry. There you go. This is your final answer for this question. This one's pretty simple. 2 plus square root of -1 square root of -1 is just I. So you can work that by yourself. 3 plus square root of -8 minus square root of -32. Well, square root of -8 we've already established that's 2I square root of 2. Right? And then square root of -32, it's 2I square root of -8. Square root of you can take a 4 out of square root of 32. It will be 4 square root of 2. So this is 4I square root of 2. So if you have 2I square root of 2, subtract 4I square root of 2, you'll get minus 2I square root of 2, which will give you 3 minus 2I square root of 2. And then this is square root of -7 squared. This is basically I square root of 7 squared. When you square I, you get negative. Or you can just look at this and you can just know it's that, right? You get rid of the square root and you get rid of the square, which would just give you -7. And 3 times square root of -4, square root of -4 is 2I. Right, I've already told you this. Square root of -4 is 2I, so it's 3 times 2I, which is 6I. Right, and if we simplify this, we'll get, I'm going to do it really quickly. It will be, actually, I can't do this really quickly. It will be, the bottom would be 49 minus 36I squared, which is 85. And then the top, I need to do 3 minus 2I square root of 2. Multiply that by -7 minus 6I. Oh god, this is getting really messy. Which will give you minus 21 plus 12I squared square root of 2, which is minus 12I minus 12 square root of 2. So it'll get you minus 21 minus 12 square root of 2 over 85, and then it'll get you plus 14i squared of 2 plus 18i. So plus 14 square root of 2 plus 18 over 85. And then I'm going to move this answer a little bit to the left. I. And that's it. That was a long question. So if you multiply this, you would get the answer would be 8 plus 4i, right? I think, yeah, that should be the answer. If it's wrong, put them down in the comments. I will really appreciate it. Yeah, it'll be really nice of you to put it down in the comments. That's 2, and then that's I, so that's just I squared root of 2. That's 5. You'll get 5 at the bottom, and then in the top you'll get 10. You'll get 10 plus 5i, I think. This is actually a nice equation. Oh god. This is actually a nice equation, because this divides really well. 10 divided by 5 is 2 plus I. Got it. That's it. That's it. Wait. Is it? This is a miracle. Wait. 4i 10. Yeah, this is literally. That's it. That's it. This is actually a nice equation. I did not know that. Okay, anyways. Let's go to the complex plane now. I'm gonna go through this really quick because it's really straightforward. Complex plane, there's a plus bi. The x-axis is a and the y-axis is b. Someone made this up. I don't know, but we'll just do it, right? Let's do it. So 2 plus 6i is 1, 2, 3, 4, 5, 6, right here. Oh no, right here, right here. Minus 1 minus 2i is minus 1, 1, 2, right? Don't make sure you don't put the I, okay? Make sure you don't put the I and confuse you, right? It's not minus 1, minus 2, and then I has its own axis. No, it's just A and then B, right? So minus plus positive 6, and then minus I, so it'll be right here, right? So 1, 2, and 3 points. Next. So absolute value of the complex number is the distance to the center, and the absolute value of complex number is also known as the magnitude of the complex number, and the magnitude of the complex number is the distance of the complex number from the origin. It's like a vector. We'll talk about vectors later. I don't want to waste your time. So the absolute value of z is equal to a squared plus b squared in the a plus bi. And in this case, it's 3, 5, and 3i, so it's 34. So absolute value of the complex number 3 plus 4i is 3 squared, right? Absolute is square root of 3 squared plus 4 squared, which is equal to square root of 25, which is equal to 5. That's it. I'll let you do these two. So distance and midpoint works the exact same between two complex numbers when you have a and b. So in this case, it will be, well, the difference between 2 and 7 is 5. So it will be 5 squared. And then I and then minus 7. That's 1 and minus 7. And the distance between them two is 8. 8 squared and 5 squared will be square root of 89. Right? So this is the exact same. 5 and 2 is 3 squared. This is just the distance. We'll be doing the midpoint later. 3 squared minus 4, that's 14 squared. And then 3 squared and 14 squared, that's 196, so square root of 205. Oh god, okay, so those are the distances. What are the midpoints? The midpoints is just the average of the two. The 2 plus 7 is 9 divided by 2 is 4.5. I minus 7 is minus 6 divided by 2 is minus 3. That's it. 5 plus, I'll let you do the midpoint of this. I'm going to return back to this. Now we have, this is the square root of square root of 3 squared plus 8 squared. Square root of 3 squared is 3. 8 squared is 64, so that's square root of 67. And finally, 3 minus I squared of 5, so this would just be 3 squared plus square root of 5 squared, which is equal to square root of 9 plus 5, which is equal to 14, square root of 14. Right, this is 5 plus 2 divided by 2 is 3.5, minus 4 plus 10 divided by 2 is plus 3i. And that's it. Right, that was the quickest I've gone through 1.5 slides in a long time. If I can draw this 3. I can't draw this 3. There you go. Okay, there you go. Next slide. So this is the important stuff in 2.6. I've already told you about this. This is called the conjugate. And the conjugate of a complex number is the number with the opposite sign of the imaginary constant. But it can really just be the opposite sign of the real one as well. That will also eliminate the a plus bi, the abi minus abi component of the equation. So, and also in order, right? So we have this difference of squares thing, right? Difference of two squares. And in order for an expression to be the polynomial, which is have real roots as its has real numbers as its coefficients, we have to have an imaginary root cancel with another imaginary root that's its conjugate. So for this smallest polynomial, it will be x minus 3 plus 2i, x minus 3 minus 2i, right? Because the roots means they're equal to 0, so 3 plus 2i minus 3 plus 2i is just 0. And then we have to have its conjugate as well, x minus 4, x plus 2. Right? You could work this out. It'll take pretty long. I don't really want to open this. I'll just open it just for the... but I expect you to already know how to open this. So that's just, this is just x squared. And then this is, let's say this is minus 3 minus 2i. And this is minus 3 plus 2i. So minus 3x minus 3x minus 6x. You could expand them all, but I'm just doing it the quick way. All the i's will disappear, so we have this minus 3 right here. Multiply them together, you'll get add 9. And then you have minus 2i times 2i, which is 4i squared. Minus 4i squared is plus 4, so it'll be plus 13. And then we can add these together, multiply these together, which will give us x to the 4 minus 8x to the third. This is plus 12x squared plus 13x squared minus 8x squared, so that's plus 17x squared. This is minus 26 minus 48, plus 48 minus 26, which is plus 22x. And then this is minus 13 minus 8, which 13 times minus 8, which is 104. So this is our final polynomial. Right? It's a disgusting polynomial, but there's more disgusting ones. There's more disgusting polynomials later in this. It's already been 23 minutes. Oh god. Every polynomial of degree n has n complex roots. That's the fundamental theorem of algebra, and the fundamental theorem of algebra is really important as to the well-being of algebra itself, but it's really not that important for school. But because of this fundamental theorem of algebra, I can prove the next theorem is called linear factorization theorem. And since they have n complex roots, you can write them all as x minus a1 plus b1i, x minus something a plus bi, x minus a plus bi, x minus a plus bi. Keep going for the whole polynomial. And every polynomial has these types of roots, and there is no prime polynomial that doesn't have a root of a plus bi, right? However, if the polynomial has complex coefficients, it's not a polynomial. So for example, is this I'll go to this right now. So is this a polynomial? X minus 3i, x plus I, x plus 2i. We can't really decide if this is a polynomial yet, and the reason why is if we like the conjugates, we're not sure if one of them actually gives a conjugate or not. But I can just tell that this is sus, right? This is sus. It looks sus right now, right? It probably isn't. right? Minus 3ix plus ix, that's minus 2ix. And then minus 3i times I is minus 3i squared, minus 3i squared. So this will be plus 3. This will be plus 3. And right away, you can notice that this will not work because 3 times 2i is 6i, and that's a imaginary constant. So this won't work, right? This is not a polynomial. However, if you look at this, is this a polynomial? I'll let you find out. But these two are definitely polynomials, right? 3x plus 2i, 3x minus 2i, and I just put this in just to waste your time. I times negative I is just negative I squared. This is negative I squared, and negative I squared is 1. So 1 times 3x plus 2i. I didn't actually put it in to waste your time. I actually tried to like make it a problem, but make it like a 4th degree polynomial, but I just failed miserably. So that's just 9x squared, and then since it's a difference of squares, difference of 2 squares, it crosses off, and then minus 4i squared. Minus 4i squared is plus 4. So this is the final equation. This, now we have x plus 3i, x minus 3i. We'll just do that. Just x squared minus 9i squared minus 9. No, plus 9, I mean, because minus 9i squared is plus 9. And then times by x plus 5, x minus 7. You should know how to do that already. I'll do the other problem now for you to check that answer. So this right here is this right here will condense to a this will condense to a real x, like a 9x squared and plus 25, right? So that's why, and then there's a 9x squared plus 25, there's a 2x plus 1, there's an x minus 6, so this is real. This is a real, and this is a polynomial, right? Okay, we'll move on to the other question. So x squared plus 9, x plus 5, x minus 7, this is just x squared minus 2x minus 35. Right, multiply by that, that's x to the 4th power minus 2x to the 3rd power minus 35x squared plus 9x squared minus 26x squared, and then minus 18x, and then minus 350. And that's your polynomial right there. Alright, okay, I actually gotta go address this now. Note, complex numbers do not mean real only or imaginary only. It can be real. It does not mean real and imaginary. It can be real only and imaginary only. It can be 4i can be a complex number, 3 can be a complex number, pi is a complex number, right? Complex numbers are in the form a plus bi, but b can be 0 and a can be 0. 0 is a complex number, right? It seems simple, but 0 is a complex number. So complex numbers are real numbers and imaginary numbers and a combination of those. Write a polynomial with lowest degree with the given multiplicities and roots. Let's try. We have 3 plus I, multiplicity 1, multiplicity 2, minus 1, multiplicity 2. So let's do it. This is 3 plus 1 is multiplicity 1. Honestly, I don't even want to do these questions. 3 plus 1 is multiplicity 1, so we have 3 minus 1 as one of the roots as well. So we have x plus 3 plus 1, x minus 3 plus 1, 3 plus I mean, x minus 3 minus I, x minus 4 squared, and then x plus 1 squared. And I'm not going to expand it, right? You don't have to expand it, unless you want to, as an exercise, just for fun. This is x minus 4 minus 5i, but squared. This is squared. This is a little weird. I'll tell you why this is a little weird later. But we can just do this. X plus 2 to the 3rd power. X plus 8 to the 1st power. We're going to expand this, and we're going to see if there's a better way to have a lower degree with the multiplicity of 2. So we'll expand this. We'll get x squared minus 8x I'm sorry, I can work this out by myself, right? Minus 4 times minus 4 is plus 16, and then plus 5i squared is plus 25i squared, and plus 25i squared is minus 25, so minus 9. And we're not done yet, right? We're not done yet because there's still 4 times minus 5i. No, wait, no. Minus 4 times 5i, and then minus 4 times 5i, which is minus 40i. And then there's still x times minus 5i and x times minus 5i, which is minus 10i. ix, right? Ix. Right, so the imaginary number is now part of the x, which makes it a lot harder to deal with. Right, so this is our polynomial right now. Can we find one thing, just one thing that can get rid of this monstrosity, right? Can get rid of the minus 40i and the minus 10ix. And I challenge you to find one thing, but as of right now, I want to save time, so let's just say we can't, and we'll have x plus x minus 4 plus 5i, and we'll put that to the squared as well. So this will be x minus 4 minus 5i squared, x minus 4 plus 5i squared, x plus 2 squared, x plus 6. Okay, time to do questions from the book. Now we have question 48 for 2.6, which is, oh god. Question 48 for 2.6 is it possible to find a polynomial f of x of degree 4 with real coefficients that have zeros of 1 plus 3i and 1 minus I? 1 plus 3i, 1 minus I. Right? Is it possible for degree 4? Actually, we gotta have x minus because this is a polynomial. Right? We have x minus, and then it's 1 minus I, right? Okay. So we have this polynomial right here. Is it possible? Well, just by regular logic, by what I've told you, it is possible because all you need to add are these. Right now you have 1 plus I, x minus 1 minus 3i, and then x minus 1 plus I in order to make this to make it real. So it is possible, right? It's possible. 53, multiple choice. Let z be a non-real complex number, and z with a line be its complex conjugate. Which of these is not a real number? And the first is the a, which is z plus z with a line. So that's a plus bi, right? Z is just any complex number plus a minus bi. And right away you can see that that option doesn't work. What about z? We already established a z with a line through it. We already established that this is a real number, so this is a real number. The absolute value of z conjugate. The absolute value is always real because it's a squared plus b squared. 1 over the absolute value. Well, I already said it. The absolute value is always real because it's 1. Right? When I put this symbol, it means exists in the real sense, right? So and it's real, right? Z squared. Z squared is wrong. And you can prove why. It's easy. Just take a plus bi times a plus bi, expand it. You will get a squared plus 2abi minus b squared. Right? And this 2abi is automatically a red flag. So E will not give you a complex number. Unless if B is 0, right? So E will not give you a complex number. E. 56. Assume that 1 plus 2i is a 0 of the polynomial with f with real coefficients. I'm hoping you follow the book because I'm not writing this thing down. Which of these is not statements is not true? 1x minus 1 plus 2i is a factor of f of x. Yes, it is. X squared minus 2x plus 5 is a factor of f of x. Well, let's see if it's actually a factor of f of x. So we take x minus 1 plus 2i, x minus 1 minus 2i, if we open this up, we'll have x squared minus 2x, right? It looks promising. Minus 1 times minus 1 is plus 1, and then minus 2i times plus 2i, right? Minus 1 minus 2i. I'm gonna expand this out for you guys, easier to see because you can't see it like me. Minus 2i times 2i is minus 4i squared, which is plus 4. So this is actually a factor. Yes, D is correct. X minus 1 minus 2i is a factor. Yes, that's correct. 1 minus 2i is a 0 of f. That's correct. That leaves E wrong. And if you take E, the number of non-real complex zeros of x could be 1. It couldn't be 1 because every single time you have a complex number, you have to have a non-complex. You have to have its conjugate in order for it to be a polynomial. Question 66. Find the 3 cubed roots of 8 by solving x cubed equals 8. X cubed equals 8. What's the first cube root? It's x equals 2. That's obvious enough. What are the other 2 cube roots of x cubed equals 8? Well, we can take 8, we can move it like to the left. We'll have x cubed minus 8 is equal to 2. Is equal to 0. And if you're knowledgeable in factoring, you will be able to factor this x cubed minus 8. You will get x plus 2, and then you'll get x squared plus 2x. Actually, no, that's wrong. You'll get x minus 2, and then you'll get x squared plus 2x plus 4. And that is your factoring, right? As minus 4. Wait, no, that's x to the cube. That's correct. And then we have x4x minus 2. Yeah, that's correct. Okay, that's equal to 0. So x is equal to 2. That's our first choice. But our second choice is x squared plus 2x plus 4 is equal to 0. And we can do this by completing the square. We'll have x squared plus 2x plus 1 plus 3 is equal to 0. I don't like quadratic formula most of the time. So x plus 1 squared plus 3 is equal to 0. So then your final result is so square root of minus 3. Your final result is minus 1 square root of minus 1 plus or minus square root of minus 3, which is equal to minus 1 plus or minus I square root of 3. And those are your 3 results to x equals 2. So your 3 results are 2, minus 1 plus I square root of 3, minus 1 minus I square root of 3. Right, it's really interesting why you get these minus 1s and stuff, but you get them. So, fine. Okay, I really don't want to do this. I threw myself a curveball by getting such giving such a damn hard question to myself. Basically, what you want to find is 3 real roots. If you can do this, I'll probably do it the next half of the recording, but I'm not going to do this right now. Rational functions. Oh, sprinkle. Okay. Rational functions is in the form p of x over q of x, where p of x and q of x are polynomial. Which are rational functions. I'll let you figure this out. This is a challenge right here. Challenge, right? I'll give the answer in about a minute. Which are rational functions? Is this a rational function? Well, square root of x plus 9, is that a rational function? Even if I put a squared here, it's not a rational function. Not a rational function. Because square root of x plus square root plus 9 will not simplify. Is this a rational function? Well, this is a polynomial and this is a polynomial. So yes, it is. Right, this is the reciprocal function right here, and we have to find the we're going to find transformations with those. And this is your challenge right here, and I already set your challenge up. This is a polynomial function. This is a rational function, yeah, of more than one variable. But we won't want to talk about that yet, because these are still polynomials. You learned from integrated math 1. These are still polynomials. So these are your features right here of the 1 over x, right? The 1 over x, I'm going to put sprinkles around the x squared, x cubed, as log x, whatever we get to as well, ECX, ATX, they're all gonna get sprinkled. But this is the overview of what the function is. And you could see I labeled this and said odd function because it is an odd function, because it satisfies this rule where minus f of x equal to. And this is how the fully transformed function would look like. So I'm going to try to get this form, even though I probably won't. Let's put a 2 right here so that we can actually get the form. So describe the transformations. What do you do when you get the what do you do to get the transformation? Is you divide the top by the bottom, right? So I'll do this first because this is the harder one. What I can do is put both sides under 2x minus 3, or I can just leave the 5 kind of like hanging right here, and do this division. So this division might actually look quite hard, but it's actually not that hard. All you need to do is, well, 12x minus 8 over 2x minus 3. 2x minus 3 you can divide by 2. You can do this 1/2 times 2x minus 8. You can do long division as well, but I'm showing an easier method. We'll give you this, and then you can synthetically divide. Right, and then 3/2, and then 3/2 times 12 is 18. No, 8. Bring the 12 down, and then do the 18. And then 3/2 times 10 is 5. No, 18 times negative 8. 18 plus negative 8 is 10. 10, and then yeah, it's just 10, right? You don't have to times by 3/2 anymore. So this will give you this remainder. No, this is the result, and this is the remainder. So we'll have this is equal to 1/2 times 12. 1/2 times 12 plus 10 over x minus 3/2, and it looks like I'm making it like more confusing, but I'm really am not trying to. Okay, we can combine this together, and then we can manipulate the function to get 1/2 times 12 is 6 plus 5, that's 11, right? And then 1/2 times this is 5, right? So it'll be 11 plus 5 over x minus 3/2. Right, that's your function, right? You might get this, you might not get this. You could put the 1/2 outside and get the 10, but b over minus a is normally a vertical stretch just by itself. So this would be shift up 11, vertically stretch by 5, and then move to the right by 3/2. Right, so I tasked you with doing this, right? You can just use the same division method that I used. You'll get 3x, so you'll get 3 minus 11 over x plus 2. So this is 3 up, reflect over the x-axis, vertically stretch by 11. Actually, first of all, is move to the left by 2, then vertically stretch by 11, then move reflect it across the x-axis, then add 3, or move 3 up, right? That's it for number 9. 3 types of asymptotes. There are 3 types of asymptotes. I won't go through the first 2 really fast. I'll go through the first 2 really fast. Vertical, simple enough, just 2 lines. Horizontal, vertical is denominator equal to 0 and do everything. Horizontal is if the top is lower power than the bottom will race faster than the top. Therefore, the bottom will be way bigger than the top when it gets to infinity, and it will approach 0. If they're the same, so x squared and x squared, you just take the ratios of the two, because they go both to the same. They both go to the same speed. It's just one goes 2 times as fast and one goes 7 times as fast. So we take 2 and then we take 7 for this case, right? This is a slant asymptote. What's a slant asymptote? A slant asymptote is it's like one of these. Wait. It's one of these, right? It's one of these asymptotes. It's the rational function doesn't really reach. It doesn't reach a linear line, or it doesn't reach a quadratic line. right? Like a big line. There can be a function that looks like this. Is what I'm trying to say, right? There can be a function that looks like this. Like something ridiculous like this. There can be a function that looks like that, right? And the quadratic will represent the asymptote. And there's only one of these asymptotes in the function. So what you do is you divide. You divide, and that's how you get the asymptote. So right here I divided, and then you don't take the remainder, because whenever you take the remainder to infinity, you'll get 0. See, whenever you take the remainder to infinity like this, you'll get 0. So you just take this, right? The bit that you get off it, 3x. So then you have an asymptote at y equals 3. Right? For this case, yeah, for this case, I'll just delete this. This needs to be erased out of my existence. Okay, so for this case right here, we'll just do the long division, or we can do the hack again and do this, right, over 1/4, so that'll be x minus 5/4. So then now you can just do your synthetic division and like forget about it. It'll be a little bit messy. 3, but all you need is this term and this term. You don't need the remainder. So 3 times 5/4, that's 15/4, and then 15/4 minus 1 is 11/4, and then 11/4 you could continue the thing, but it's not necessary. You'll get 89/16 at the end. Right, so the slant asymptote is, you can know it will be 3x plus 11/4. That's your slant asymptote for that one. This one, end behavior asymptote can be a slant asymptote, but it can also just be a horizontal asymptote. This one you don't have to do anything, because that's x squared, that's x cubed, that's x cubed. So the horizontal asymptote is y equals 2. This is y equals 3x plus 11/4. Right, and you don't actually have to account for this. Wait, do you? You might have to account for this 1/4. I'm not sure actually. I think you do have to account for the 1/4, because simply it's just a ratio of the two. It's just a ratio of the two functions. So whenever you divide this, like actually really divide this, you will get the 3/4. So this is not actually the slant asymptote. The slant asymptote is 3/4 x plus 11/16. That's the slant asymptote of the function. Right, this is not the slant asymptote, because you have to multiply by 1/4. Next, analysis. Yay! We're gonna analyze some functions. We're gonna draw them, right? So this one's really nice. This one's really nice because it can be factored, right? I'll just factor this right now. This is x minus 2, x plus 1. The bottom is x minus 4, x plus 2. Done, right? And this is simple. This is a simple enough function because it has vertical asymptotes at 4 and minus 2. So this is x equals minus 2. And this is x equals 4. Right, and then we have our y and behavior, which is going to be 1, right? But how is it going to look like? Well, let's see. Let's say the number is below 2, right? We have a number below 2. Let's see what we're going to get from a number below 2. Let's try actually the nicest number that I want to try first is 0, right? So we'll have 0 minus 0 will get you minus 2 plus 1, which is minus 2 over minus 4 plus 2, which is minus 2, which is 1, right? So 0 will get you, no, wait, I'm drunk, I'm sorry, minus 4 times 2, which is minus 8, which will get you 1/4. So 0 will get you 1/4, right? It'll get you 1/4, which is about here. So 0, 1/4. Let's try a bigger number, like 2, right? 2 minus 2 is 0. 2 minus 2 is 0, so the function is 0 at 2. You can also find zeros. pretty easily with this type of form, right? -1, 0 at -1. So rough curve you can already draw. It looks kind of like this, right? So this part's already like this, right? What will we have over here? Let's take a big number now. Let's take 5. 5 minus 2, 5 plus 1. That's 3 times 6 is 18. So we'll have 5 now, right? 5, 5, 5, and 5. 5 minus 2, 5 plus 1, that's 18. Over 5 minus 4 and 5 plus 2, that's 7. That's a big number. That's a big number, yeah. So 5 will get you 18 over 7. 5, 18 over 7. That's like right here. So you can now assume that any number that's bigger than 5, since we got all positives here, any number that's bigger than 5 will still continue giving you all positives. Therefore, the graph will look like this. Because the horizontal asymptote and the vertical asymptote. I can also assume that a graph looks like this if the graph looks like this. But we'll just make sure, right? Okay, let's try -3. So -3 will get you -5, -2. -5 times -2 is positive 10 over -7. Right? No, -3. You'll get -7 times -1, which is positive 7. So positive 10 over 7. That's also bigger than the asymptote of y equals 1. So this is what the graph will look like. And we could do some analysis to say that limit x approaches infinity, limit x approaches negative infinity, limit as your ass. I don't know, but I'm not going to do any of that. Let's not do any of that. So this is our next function. I think this will be the last function. I will not do. Holy crap! Actually, I'll let you do this. I'll probably post it in the comments. Right? Do this. I'll post the answer in the comments in about, I don't know, the review day. This is simpler, so I want to do this. This has a really weird horizontal asymptote because this is x to the 5th and this is x. So we'll do our division, right? So in synthetic division, that's 1, 0, 0, 0, 0, and -1 because you have to have 1 for every term. And then this is just -2. That'll give you 1, -2, -2, 4, 4, -8, -8, 16, 16, -32, -33. So your final, your asymptote will be this, which I don't want to draw. I don't want to draw this at all. Oh wait, this is a plus. I don't want to draw this at all, right? Okay, and we don't need to add the -33, right? So all we know that this is this is an asymptote at x equals 2. No, at x equals -2, I mean. So we'll have this, and we'll have x to the 5th power -1. And we'll have this as the second asymptote, right? So I'm literally going to go to Desmos and try to graph this right now because this is a ridiculous graph. Let's go. Right, Desmos. This is a ridiculous graph. Absolutely ridiculous. I'm not going to graph in my graphing calculator, it'll take longer. X to the 4th minus 2x to the 3rd plus 4x squared minus 8x plus 16. This is your function. Wait, no. Oh god. Okay, it's kind of like a funky. Okay, it looks kind of like this. This is your second asymptote right here. It crosses at 16, obviously. Duh. Wait, why the heck do I have this? No, okay, wait. Okay, is it acting weird? No, it's not. Okay, good. We have this. This is your asymptote. This is what it looks like. Right? That's what your asymptote looks like. So, your function will be x to the 5th minus 1. So you know what makes that 0. That's 1. Right? So it'll look the 1 will be somewhere right here. And then there's a lot of other things that make it 0. But the 1's right here, and then -1 will works as well. That's a good point. -1. -1 is -2. -1 plus 2 is 1. So that'll be 1 minus 1 minus 2. minus 1, minus 2. That'll be something like this. So it'll look really funky. It'll probably either look actually let's make it bigger. The bigger the function, we're going to get we're going to put 0 in here. 0 minus 1, 0 plus 2, which is minus 1/2. So you'll get something like right here. This is a really weird function. Sometimes functions don't follow their asymptotes, and it's really weird. So x to the 5th minus 1, let's put a real, like the bigger the number that you get, the bigger it will grow. So it'll probably look something like this. That's unless if the graph cheeses me. And then this will probably look something like this, because as we get closer to the, actually no, it won't, because as we get closer to the function, this will get smaller. Actually, wait, maybe it will. Yeah, it will. It will. Okay, so it'll be like this, right? And then it'll go up like that, right? This is irrelevant, absolutely irrelevant, right? Or maybe it is. Maybe it is relevant, and I just haven't looked at the function enough yet. Maybe the graph of the function is actually like this, where it reaches this, at a point, right? So it'll probably look something like this. This graph right here, what does the graph look like on the left? That's minus. Well, let's test it out. Minus 3 plus 2 is minus 1. Minus 3, that's minus 244. So it'll be big positive, and then the bigger it gets, the bigger positive it'll get. So and then as it reaches really close to 0, it'll probably get even more positive. So this is probably what I'm predicting the graph to be. Right, this is what the graph I think will be. This is not what this is not what it might actually not be like this, but this is what I think the graph will be. Let me see if the graph actually is like this. How long have I been recording for? 57 minutes. I will cut some of this off. I'm sorry. X to the 5th minus 1 over x plus 2. Right, is that it? Is that literally it? X to the 5th minus 1 over x plus 2. Let me do graph settings. Let me zoom the x-axis to minus 5 to 5. Let me zoom the y-axis to minus 1000, and then positive 1000. Okay, so this is what it'll look like. I'm gonna take a picture right now, and I'm gonna copy it in here. Okay, you could stop if you don't. You could skip to this point if you don't want me to ramble. Right, this is what the graph looks like right here. Right, I'm sorry my words go over it. I'm just gonna leave some of this synthetic division right here. It's not useful. And it looks pretty accurate. I'm pretty proud of myself for getting this. I don't know how I got this, but this is what the graph looks like, and it touches its lowest point at like y equals 200. It's a huge graph. I'm pretty proud of myself for getting this type of graph, even though it's not really close. Right, the correct graph. I'm gonna draw the correct graph over my wrong graph. Right, this is my correct graph. This is the correct graph. That's the correct graph. And this side is correct. This side's absolutely correct. Right? It's pretty much flawless, except this has to be a little closer to the actual graph. I'll draw that. There you go. So we are at 2.8 now, and if you are at 2.7 and you don't want to go any further than 2.7, that's fine. But we're gonna be doing 2.8. So we have extraneous solutions, and it's one of the triggers whenever you're trying to do whenever you're trying to solve a function. So I have this function right here. For example, take solve an equation. I mean, take for example, square root of 2x minus 5 plus 4 is equal to x. Right? When you do all of this, 2x minus 5 is equal to x minus 4, and you can just square. You can square this and square this. You'll get this, this, and then this. But when you check them, the 7 option works, but the 3 option doesn't work. Right? 2 times 3, 6 minus 5, that's 1. Square root of 1 is 1. 1 plus 4 does not equal to 3. Right? That doesn't make sense. So well, we gotta take into account of the solutions that don't make sense, and then we have to take them off, just completely take them off, because there's some fault probably in this step that makes the solution have the equation have more than one solution, right? In this step, when you're squaring everything, you don't actually account for any of the negatives, so it's a little bit iffy, right? But we're not going to do radicals that often. We're going to do more of this. It's going to be a solution. It's going to be an extraneous solution in these formats, right? If there are solutions, we can discount them if they aren't solutions, and we will include them if they are, right? For example, in this, in this question, what's the common denominator of x and x plus 1? Now, actually, we can simplify this, right? This is x and this is x plus 1, and this is x and x plus 1. So the common denominator of these two fractions are x times x plus 1, because none of them are common factors. None of them are big. They're relatively prime. They don't have factors that they share, right? So what are you going to put in here? Well, this is 3 over x, where you multiply by x plus 1 over x plus 1. Like this, you'll get 3 times x plus 1. And then over here you multiply by x. See, if you do this, you're actually multiplying by 1. But because we're adding x and the x plus 1 in this side, we can finally have it so that there's x times x plus 1 here, and there's x times x plus 1 here as well. And you can add this to 4x, and that'll give you 3 over x times x plus 1. Right? Since they're both the same denominator, we can just yeet the denominator. We'll have x plus 1 plus 4x is equal to 3. And then we'll have 3x plus 4x, that's 7x is 0. Right? I'm doing it pretty quick. That's 3. Right? That's 3, and that's 3x. So this is 3, and that's 3. So it goes away. 7x is equal to 0, x equals 0. X is equal to 0, but if you put this 0 back into the equation, you could see that there's so many things wrong with putting 0 into this equation. For 1, you'll get 3 over 0 plus 4 over 1 equals 3 over 0, which this doesn't make sense at all. Right? 3 over 0 plus 4 over 1 is not equal to 3 over 0. It makes sense because 3 divided by 0 is infinity or negative infinity. According to which side you go to, it's undefined. It's asymptotic. There's no actual solution to this equation, right? So those are the things that you got to keep in mind when you're solving these equations. Is sometimes it doesn't go as nice as you want it to go. So next we have 2 minus 1 over x plus 1 is equal to 1 over x squared plus x. X squared plus x can be factored into x and x plus 1, like this. Right? So now we have 1 over x times x plus 1. So we want all of them to have this x over x plus 1 denominator because it will be much easier to deal with. So we can just multiply by x on this side, multiply by x up here, and then we can multiply this whole thing by x plus 1. I should stop putting the parentheses around the x. There we go. Now we'll have 2 times x plus 1 over x times x plus 1. Actually, I can put this whole thing underneath because we can just do subtract x like that, and then that will equal to 1 over x times x plus 1. So our equation is 2 times x times x plus 1. This is x squared plus x, that's 2x squared plus 2x. And then minus x is equal to 1. And you can do this because x times x plus 1 here and x times x plus 1 here, they're both their same denominator, so you can just set that equality. So 2x squared plus x, and then we can do minus 1, throw minus 1 over there, and then you can factor this. You'll end up getting 2x plus 2x minus 1, and then x plus 1, I think. Yeah, that's what you'll be getting. That's equal to 0, and so we have x is equal to 1/2 and x is equal to minus 1. So which one of these works, right? Is what we're trying to figure out. So let's write the equation again. We have 2 minus 1 over x plus 1 is equal to 1 over x squared plus x. And if you're observant, you can automatically see that minus 1 is automatically out of the table, because minus 1 plus 1 is 0, and you can't have 0. We could go checking the 1/2, and in fact we are going to go checking. We are going to go to check the 1/2. We're going to check the 1/2 right now. It'll be 2 minus 1 over 1/2 plus 1 is 3/2, so 2/3 will be this fraction. 3/2 is equal to 1 over 1/2 squared, 1/4 plus 1/2. So this will give you, this is really messy. That's what it is. This will give you 2 minus 2/3 is equal to, this right here, 1/4 plus 1/2 is 3/4, and whenever you flip it, it's 4/3. So this is correct. Next question is harder. Oh god, it's a little harder. Question 41 from 2.8. So we're gonna go to 2.8 right now. I'm gonna go to 2.8 right now. It is question 41. Swimming pool drainage. Let drains A and B are used to empty a swimming pool. Right, so we have a swimming pool. I'm gonna B alone to empty the pool. So this isn't even supposed to be. Okay, so it'll be the time, t be the time, so that's 1 over t is equal to b, right? To express as a function of t, the part d of the drainage that can be done in 1 hour with both drains open at the same time. So it'll be 1 over 4.75 plus 1 over t, right? And it's done in 1 hour, so t is equal to 1 hour. We don't have to multiply anything. It'll just be d is equal to, this is equal to, you gotta multiply t on both sides here, and then 4.75 here. So you'll get t plus 4.75 over 4.75t. Right? Find graphically the time it takes for drain B alone to empty the pool if both drains, when open at the same time, can empty the pool in 2.6 hours. I'm trying to do 2.6 plus 4.75 over 4.75 times 2.6, and then whatever answer you get for this, right? This answer is the amount of time that both drains take. You subtract from 1.475, and then this is your answer, right? 1.475, and that will give you 1 over t. So t is just, you flip this. So whatever answer you get, a equals 1 over t, t equals 1 over a, and that's the answer of the equation. But I'm not going to calculate it because it will take too much time. This review is already taking too much time, so there you go. Inequalities. We have to use common sense whenever we want to deal with inequalities. And the reason why is if we don't use common sense when we deal with inequalities, we won't know if it's going to be higher than 0, less than 0, dancing around 0 like the sine function. We don't know. We have to use common sense, especially the signage, right? So I'm going to draw a line right here. And there's going to be x squared minus 7x plus 10, which can be factored to x squared, no, to x minus 2, and then x minus 5, right? So I have these two boundaries, right? The 2 and then the 5, and then this is 0. No, the 0 doesn't even matter. So first of all, what happens when you are less than 2? What happens when your result is less than 2? Well, let's see, right? If you have 0 in here, you'll have minus 2 times minus 5. If you have 1 in here, you have minus 1 times minus 4. They will both be minus, right? When you go here, they will both be minus. It keeps becoming minus, and since it's both minus, the result will always be positive. So minus times minus is positive. What if we are in between 2 and 5? Let's say 3. 3 minus 2 is 1, but 3 minus 5 is negative 2. Right? 3 minus 2 is 1, positive 1, negative 2. 4, positive 2, and negative 1. Right? There will be a positive and then a negative if you are between 2 and 5, because this will be positive and this will be negative. So this is equal to negative. And then 5, when it's bigger than 5, well, let's put 6 in here. We'll have plus 4 and plus 1. Right? If it's bigger than 5, they'll both be positive, so it'll be positive. So plus. So we have minus minus and plus plus are both positive, are both more than 0. So x squared minus 7x plus 10 is higher than 0. We have to have x is smaller than 2 or x is bigger than 5. Or we could write an interval notation, but I'm not going to. And if you want it less than 0, you will have 2 is in between, x is in between 5. And that's it. We're done. Solve for this function. So we'll do the exact same thing. We'll subtract everything to the other side. We'll have 0, right? So 5x minus 36 is higher than 0. And then we'll have x minus 9 times x minus 4 is higher than 0. And just by looking at this first term right here, you're already going to know the end behavior. And just by the end behavior, you can already tell how the function is going to go, right? It's called Descartes rule of signs. Descartes rule of signs. So every time there's a 0, the function has to go positive, then negative, then positive, then negative, then positive, then negative, or the other way around: negative, positive, negative, positive. It cannot be negative, 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 negative. It can't be like that, right? Or if it hits 0 exactly at that point, so a multiplicity of 2, 4, 6, 8, then it will hit 0, right? But if there's no multiplicity of 2, 4, 6, or 8, it goes positive, negative, positive, negative. So in this thing, you already know that the end behavior is going to be plus and plus. So we can draw this line. We have 4 and then 9. We know that's plus. We know this is plus. So therefore, the middle must be minus, because one of them is negative and one of them will be positive. So this will satisfy whenever x is higher than 0. No, whenever x is higher than 9 or x is lower than 4. And those are the two solutions, right? Next, analysis to solve inequality. Analysis, we're going to be doing some analysis, but I pretty much already told you the analysis that I was going to tell you from previous slide. So what we do is we just do it. We just put x plus 5 and then x minus 3, and then the roots are -5 and 3, so we just make a number line, and then put -5 here, and then put 3 over here. And then when is it higher than 0? It's higher than 0 when it's positive. So when is this positive? The x squared plus 4 we don't have to worry about, and the reason why is x squared is always positive. It's always positive. So if it's 0, it'll be positive. If it's 1, it'll be positive. If it's 2, we don't have to factor into x minus 1, x plus 1 because it's not a minus, right? So so we have -5 and 3 here. And this is a x squared, and it's positive, so the end behavior will be positive, positive. So that's positive, and that's positive, so that has to be negative. Therefore, it's x when x is smaller than -5, and when x is larger than 3. That's all you have to do. You don't have to graph it. Well, you do have to graph it if they tell you to, but you don't actually have to graph the function in order for you to know that that's the inequality answer, right? Okay, sometimes it's a little tricky. For example, solve x squared plus 1 is smaller than 0. I'll let you do this. We're going to be doing these wacky ones now. The square root of x plus 3 times x minus 7 is smaller than or equal to 0. Now, there's boundaries in here, but not the way that you will think there will be. Because there's boundary, and then there's a boundary at -3, and there's a boundary at 7, right? If there's a boundary at -3, anything lower than that, let's think about like the reality of numbers. If you take a number that's lower than 3 and then you add the 3 into it, you'll get a negative number inside of a radical, and that's not allowed. So that's just nothing. Just no, it doesn't work, right? This is a little different. We have x, we have between -3 to 7. So it does work inside of the function, and then you'll get a negative and a positive, therefore it's negative. And if you put it here, then you would just get a positive, which we don't want, right? So we don't want the positive, we don't want the minus. So the x is in between 7 and -3. And how do I denote that? I'm stupid. 7, x, and then -3. Like that. And finally, solve x plus 1 square root, no, not square root, absolute value of x minus 2 is higher than or equal to 1. So we have boundaries here as well, but we have to take note that the bottom will always be positive. So our only genuine boundary is x plus 1, right? But then we have to have it higher than or equal to 1 as well, which is a little bit complicated, but we just want it to be higher than or equal to 0 right now. Because if it's not higher than or equal to 0, it won't be higher than or equal to 1. X plus 1, x minus 2, our boundary is at -1. And if it's any lower than -1, that will become negative, right? So that doesn't work. That does not work. So now we have x plus 1 over x minus 2 is higher than or equal to 1. Now we can assume that this is positive now. We can assume that this is positive because the negative answer won't work because we already assumed that whenever x is smaller than -1, it doesn't work. So now we have x plus 1 over x minus 2. Now we can solve it like a regular inequality by turning it into an equal sign, and then we'll do our analysis later. So this will give you x plus 1 is equal to x minus 2, which is undefined. What happened? So this is undefined, which means we do actually have to take the negative case now. So whenever there is an absolute value, you take the positive and the negative case, or else you will get this undefined mess, right? And then it won't work. You'll have x plus 1 over 2 minus x is equal to 1, and this is equal to x plus 1 is equal to 2 minus x, so x is equal to 1/2. 1/2. 1/2? 1/2. Yeah, okay. So then now we have another boundary at 1/2. Okay, when the numbers are bigger than 1/2, what happens? Okay, let's say we put this as 1, right? 1 plus 1 is 2. 1 minus 2 is -1. And -1 will give you a number that's well, no, 1 plus 1 is 2, 1 minus 2 is minus 1. That'll give you a number bigger than 1. That's great. Minus 1 plus 1 is 0, so that's just smaller than 1. Okay, if you put exactly 1/2 in there, you'll get 1. What if you put 0 in there? You put 0 in there, you'll get 1/2, which is smaller than 1. So everything in this doesn't work, right? You'll just have to test out some of the values, but we solved this for 1/2, so anything that's higher than 1/2 might work, right? And there's another boundary that we'll have to test it to, and it's basically just trying to keep. Actually, no, there's no other boundary we have to test it to. Everything else in this higher area is going to be higher, because if you put x equals, let's say 20, for example, you'll get 21, and then you'll get 18, which is always higher than 1, right? So the top and then the bottom will always have a difference of 3 if it's higher than 1/2. Therefore, it'll work for all numbers. So if the solution is x is higher than or equal to 1/2. Solve x squared plus 1 is smaller than 0. Well, first of all, you can already kind of notice a red flag whenever, even if you're trying to do this, right? You can notice a red flag. It's not a real number. And x squared plus 1 is smaller than 0. The function's like this, right? The function's like that. And then you have 0, which is like this. So does the function ever become 0? No, it doesn't. So there's no real solution. So you can say x doesn't belong to the real numbers, or you can say no real solution. And that's it for the whole review. It's 85 minutes long. I'm going to be putting more timestamps at the bottom if you want to go to a specific topic. And please, if you want to put my video at 2 times speed, it's totally fine, because it's too long. It's a super long video. I'm going to combine the 2.5 to 2.7 I did yesterday with this, and it's going to make a really long video. So I'll see you next time for chapter 3 review.